I'm going to talk to you about efficient self-organization, which means distributed algorithms for balanced resource allocation. And if you haven't fallen asleep yet, let's do it in another phrasing. So we're going to talk about near equitable graph coloring. Okay, so first of all, I need to do something of my checklist, which is embarrass my advisor, Professor David Peleg. So this is a joint work with Professor David, the GOAT, and for those of you who are not chronically online and does not know what GOAT is, it's the greatest of all time. Okay, so let's take a step back. I'm doing theoretical computer science, okay? You probably all wondering what that even is, okay? So our world is messy, okay? We have a very messy world. We have lots of noise, right? Lots of input, and basically science in its most pure way, it's to have an experiment which is bounded, right? We have gimel, right? And to try to understand what is true in this, contained situations. So in theoretical computer science, we do exactly the same. We define clean rules to our world, like who can communicate with who, what are the messages, how many messages we can send, what is the message size we can send. And then we try to understand within those limits what we can do, okay? Give a sharp answer. So the best analogy I can give is... Because I'm too messy, and then I'm too fucking clean. That's it, yes, thank you. Now that you're all awake, we can try to understand what equitable coloring is, okay? So as most of you are probably biologists or chemists, and I'm sorry if I'm racist towards the post audience, you do experiments, right? You have experiments. So let's imagine as a lab, we have experiments. Now, I, as a biologist, obviously, need, I don't know, a microscope for my experiments, right? And you also need a microscope for your experiment. So we have conflicts, okay? Like experiment 1 and experiment 2 require the same microscope. Experiment 4 and experiment 9, I don't know, require the same centrifuge, I guess. Bear with me here. Okay. So basically, the conflict lines are the constraint of the reader. Okay, so if we have a week, we want to do experiments in this week. I can't do experiment 4 and experiment 9 in the same day. Okay, so basically, what I need to do, I need to divide my experiments into shifts, such that each shift is without conflicts. Okay, this is exactly what a graph is. So you see those circles and those lines. The circles are our experiments, and the lines are our conflicts, okay? For the circles, we call them nodes, and for the lines, we call them edges. So don't be afraid, it's just a nice drawing, okay? With colors, all beautiful. Okay, so let's circle back. If we have these kind of experiments, we want to divide them into shifts, okay? So what we do, we try to color them, okay? Basically, every shift is a color. You see, all of the yellow experiments are without conflicts within them, which is cool. So this is what a coloring is, a coloring of a graph. Yay, we understood half of the first sentence, right? We're already making progress. Okay. So what's left to explain is what equitable is, right? We talked about equitable coloring, not just any coloring. As you can maybe see, there are many valid colorings here to be done. Okay. So basically just, let's recap. This is our graph. Edges mark pairs that cannot be together. And our coloring, our shifts for the experiments, needs to be like, so no conflicts will occur, right? No edge may sit inside one color. Amazing. So this is the most amazing graph you can see. I don't even need to talk here. There are many ways to color, but there aren't many useful ways to color. If I need to divide my experiments into shifts, it won't be useful if I have one shift with 10 experiments and the other 3 shifts with just 1 experiment. Right? I need to divide my experiments into shifts such that it will be logical, right? Every day will be about the same amount of experiments. Okay, so our ideal group size is what we try to achieve in equitable coloring. We try to achieve exactly the tasks divided into groups inside each group. Cool. Okay, so now we understood what equitable coloring is. Let's talk about distributed computing, okay? In our lab settings, I guess we have our lab head, right? The one who controls. He knows all the data, right? And he can tell you on Sunday, you on Monday. In distributed settings, we don't have this central coordinator, okay? We all have only our local views and my equipment that I need for the experiments, okay? And we need to coordinate within ourselves, which one of us in each shift. Now, we don't want it to take a lot of time, right? If it's just taking me 3 days to decide which of us is doing what when, it's not very efficient. Also, we all do it simultaneously. It's not that one talks and then all the others shut up, right? It's like we're all trying to understand each other simultaneously. So it's very hard. So now that we understood what my research is about, so what we're trying to understand in my research is where the knot can settle, okay? We have 3 things that pull us against each other. One is the time, we want to do it as efficiently as possible. The other is the palette size, the shift, the number of shifts, the number of colors. I want it to be as little shifts as possible, right? And the other is the frequencies, the number of experiments in each shift, right? Is it between 2 and 4 or, I don't know, 1 and 8? It depends. So each time we pull one, the others get pulled back, according to our results. So basically, our basic algorithm, we have a few, but our basic algorithm does three stepping stones. The one, he tries to color the vertices somehow, okay? Then, if there are large groups, he splits them. And the remaining little colors, he just reassigns them into currently okay colors. Okay, so this is the basically simple methodology we have. Obviously, it gets much more complicated than that. David can tell you after. But yeah. So different applications can choose speed, fewer groups, or tighter balance. Our results is a menu of options. And each of you can choose the dish he likes the most. Like if you need optimal timing, you have that. If you need optimal group size, you have that, etc., etc., etc. So our paper does not give one definitive answer. And this is an open question. It arises also. We have a landscape of very fast and near balanced to exactly balanced, but perfectly, and it takes a lot of time. But basically, the faster that we need the algorithm to run, the more we can expect the algorithm to not be perfectly equitable. Okay. So an open direction is, can we get closer to equitability with staying fast? And another open question is, what can we do in different models? Some different models in distributed computing. It's very interesting. Hopefully we'll find that out one day. And we have a deadline in about a week and a half, and we're still standing, so that's a win, in my opinion. Thank you.